Hey, welcome back to Hackers Teaching Hackers CTF 2021 Solve video series. In this video, we're going to be taking a look at the last reverse engineering challenge, Master Lock. Let's go ahead and get started. So with Master Lock, which I think is probably one of the most difficult challenges in the CTF, if not the first, we had two people that solved this one, and I'm very interested in hearing how they actually solved it. In my view, there's really two good ways to solve this. And we'll take a look once we kind of look at this challenge. So master lock is the binary that comes with this. I've already downloaded it. I have it listed or loaded into Binary Ninja Cloud as well as Gidra, and we'll see why in a minute. Let's go ahead and go back here. This was a core dump from running Anger with this. All right, so it says Nexus Digital Next Lock Interface, 36 concentric wafer system, completely unbreakable lockpicking layer. He didn't really say that. Wafer 1 degree rotation. Okay. That. A really high number. Okay. 3, 2. Okay, let's just say they all get this number. Really 36 of these? Yes, it's really 36 of these. Okay. Clunk, clunk, clunk. You hear blah, blah, blah. You must have gotten a rotation wrong. So this sounds bad. So basically, I think what's going to be happening, actually, I know what's going to be happening, is when you type any degree rotation in, it just stores it and doesn't actually check it until you get all 36 of them in. So there's really no way to tell whether or not you're getting close until you get all the way through them, which is an absolute pain. It would be really nice to be able to fail right away and not have to work until the end where you actually try to turn the lever and see whether or not you were right or wrong. So let's take a look at, first of all, what this looks like in Gidra. In Gidra, we have the output of that interface that we had before, clears the screen. It prints out the degree rotation. This guy right here is like our counter I, right? Like a for loop. 0x24 is 36, so it's going to run through 36 times as long as we're under 36. It'll run this. So this keeps going, and then it does scanf, so it's importing with a %LF, which is a double. It's kind of like, I don't know if the right way to think of that is a long float, but a double precision type. So which is a floating point number. So it's looking for essentially will accept decimal numbers. Okay. Then we're going to do, once all of this has been completed, it is going to go ahead and run check rotations. So the scanf is actually taking these and storing them here. Not sure why that doesn't come up in this. We might be able to fix that, but we're going to go ahead and ignore that anyway. I think it's pretty obvious from what's going on here. If the result is 0, then it's going to put this. If the result is not 0, it's going to put this and then say, welcome to the data warehouse. So let's see. It's going to say give flag, and that's going to go ahead and read the flag from the challenge server. All right. Okay. Oops, excuse me. All right. I'm used to Binary Ninja's back system. Okay, so let's go ahead and go into check rotations and see what's going on here. And this is pretty gnarly. So what's actually going on here is it's going to take our input, which is going to be a list of a pointer to a bunch of doubles, and it's going to start looking or indexing into those, and it's going to say the first double and the second double need to equal this when added together. The second double and the third double need to equal this when added together. The fifth double and the sixth double, since we index from 0, need to be 321.57. So wow. One of the ways that we can solve this is to document all of these in a nicer form. This is pretty ugly. But once we get all this information and understand that the 12th hex, the 13th hex, and the 14th hex, when the two are added together, it needs to equal this exactly. Then we can start trying to understand how we can set those constraints in order to make this work. There's a lot of stuff going on here, and this is actually a pretty hard problem to do yourself. I wouldn't want to solve this by hand. I don't know why you would attempt to do this. I don't think um, trying to knock out a few of these would work. So here, this is used twice. This value is used twice. This fourth one is used twice. This one's used twice. And I think they're a kind of random number of times. I don't know if each one is used twice or more than once or more than twice. I think they're just kind of like randomly picked when we're developing this. This one has two. It looks like most of them have two. So the two ways that I see of really solving this are one, using a constraint solver. This would be something like Microsoft Z3. The other one would be to use a symbolic executor that uses a constraint solver under the hood. This would be something like Anger or Triton, and you would ask the symbolic executor to load the binary and start executing, get to a valid location, and then check the actual state that got it there for all of the conditions that solve that. The one that I'm going to use in this video is to just use Z3, Microsoft Z3 directly. So Z3 is an SMT solver. It essentially uses theories, specific theories of numbers to solve things. There's a really good video out there, I think by somebody named John Smock, if I remember correctly. There's a really good video on SAT SMT and what it means, and I don't think it's a little bit past the scope of this particular video. But for Z3, it gives us the ability to say, I have all of these different constraints, try to find a solution for all of those constraints, and then give me back a model that satisfies that, right? We build this constraint system, and then we say, give me a model that satisfies those constraints. And the way that we're going to do that is we're going to pick these guys, and we're going to set what these things are equal to. So we're going to create a whole bunch of variables, all called these things. So we're going to say param1, param2, param3, param4, param5, param6. And then we're going to say param1 and param2 need to equal this. And then we're going to present that problem to Z3, and Z3 is going to do its magic, and it's going to solve this for us. Okay. The reason why I used Gidra is that floating point support and binary ninja for specific floating point operations is still not the best. It's getting much, much better, but you see kind of weird things like this fconvert t, and then it's like in here twice, right? So you have to kind of like mentally narrow this all down. I think it's good enough to actually use, but I like the way that Gidra is presenting it to us better, just a little bit easier to look at. So if you ever see something in one tool that you don't like, you're not really sure like what it means or what it's telling you, try a different one. Maybe there's a different output that kind of helps you a little bit better and makes a little bit more sense. When in doubt, always check the assembly, right? Okay, so let's go ahead and see what Solvescript looks like for this. First of all, we install Z3. Z3 is, again, Microsoft's SMT solver. We install the Python bindings for it, but we also install the Z3 library on the system as well, so it can use that. The set option, rational to decimal true. I was just, I do a lot of Z3 without floating point numbers and dealing with decimals or this stuff. So in those cases, I feel like I know how to use Z3 pretty well, but when it came to solving this, I just had to look up the API and try to understand how to use these reals. And it said basically to use this option. So this is something I'm using just because I read it, don't actually know what it means. So what we're going to do with Z3 is when we do Z3 import star, real means something because it comes from Z3. So what we're going to do is we're going to set up a whole bunch of reals. We're going to set up reel 1 and go all the way down to reel 36. And these reels are going to be named R01, right? So I can name this puppies, I can name it unicorns, whatever, right? But I choose to specify the same variable name as like the string reference to it. So these are reals, these are real numbers. And then S is our solver instance. So the solver instance is instantiated from that, which again comes from Z3. And then what we're going to do is we're going to set constraints on the solver. We're going to say R1 needs to be greater than 1. This rate greater than 0. If we don't do this, what ends up happening is you're going to get solutions with negative numbers, and that is not what we need for this particular problem. So again, so to do this, we can do it in a loop, but it's easier to just copy paste and do all of this. So we add all of the constraints to all of our reals that they must be over 0. This way, Z3 will never produce a solution that has any of these values as being negative, okay? Then we're going to add, and this is really nice, we can just use this sort of infix notation or logic form here where we have equals equals or not equals or whatever we need to. So we're going to say we're going to add the first real that we have and the second one, when added together, need to equal 75.4. So where does that come from? It comes from here. So what's passed into check rotations was again a pointer to all of our doubles. This is the first double, this is the second double. So it's real 1, real 2, 75.4. The second one is 92.7, and that is the third and fourth. So 3 and 4, 92.72. Did I have that right? 92.72. Okay. And then that's it. You just keep going down here. I think I did see something where there's a large one that was 89.76 with a whole bunch of zeros and a 1. 89.76, and that's not what I have here. It ends up still working. I think it's outside the bounds of precision there. I'm not sure why that happens, but we don't need to worry about it. I wonder if we add that in directly into this, if it would end up making a difference. So what we do here is once we add all of our constraints, and we add all of these constraints too, we just say you can go ahead and check the model, and if it ends up being sat, again, this is not like sat like a string, it's satisfiable. Sat means something to this. Then we can say S model and put it into the model. This whole way of doing this is a very Pythonic way that I ended up looking up to figure out how to get this to work. If I were to write this myself, I would do this and expand it out into many lines of Python. This is the nice sort of Pythonic way of doing it with a lambda function and what's called list comprehension, and then sorting all of these things. The reason why we sort them is because we need to put the solution into the problem in a very specific order, like the first rotation, second rotation. And what Z3 is going to do is just give it to us in any random order that it finds most convenient. So it's easier than rather than searching through the big list of 36 things that we just go ahead and list them in order. We then go ahead and do this R list, and then we go for each rotation in rotations, and we go ahead and set this information and then append it to the R list. And then we print out a format like an actual, what do you call it? A Python command that will spit all this stuff out for us. So it's going to print this out. So 4x in our list, and then it's going to go ahead and print it with a new line. So this means I don't have to look at one screen and then type it all in. I can just pipe this directly to netcat to the challenge, and then it'll go ahead and just work. But we'll run it on masterlock locally. If for some reason the check is not sat, it'll say unsat. So sat again is satisfiability. If it ever says unsat, it means that your problem is technically impossible, and Z3 would have generated a proof to actually show that there's no way that you can actually satisfy all of those constraints. So really, this seems like a lot of code, and it seems really complex, but this is something that you can reference in the API, and it ends up being super easy to do. This is probably the most complex thing in here, and it really just has to do with like fancy Pythonic code, right? We get all of our rotations, we format them, and then we're good to go. The model will actually have all this information for us. This is just a nice way to print everything out. All right, so let's go ahead and run this and see what we get. I already have this over on my VM. I'm gonna do hmod masterlock. Okay, there's the rotations. I am going to run Python solve Z3. It's that fast. So this is like really, really quick. We'll go ahead and just copy and paste this and run it. There we go. Welcome to the Nexus warehouse. So it wasn't able to find the flag text. I think what we can do is just replace masterlock with whatever our connection is, which is this guy. Should be. Copy that. Yep, that's right. Remove this. put that in, run it. There you go. So the flag was if you didn't use Z3 or anger, wow. So I'm really interested to see how the two people solved this actually did it. I wonder if they used anger or if they ended up using Z3 or if they just did it by hand and like toughed it out. So this is how this particular problem works. Z3 is something I think is extremely fascinating. In my line of work, I hear a lot of people say, just use a solver, use a solver, use a solver. And it's sometimes not as straightforward as that because you have to actually model an algorithm. And it's not the easiest thing to do to present stuff to Z3. So Z3 actually works usually with this something called SMT-lib. And with Python bindings, we could just do a really nice thing that's like sadd, and we don't have to learn what SMT-lib actually looks like. So it's really cool. It's something that really helps out in reverse engineering. There's really special, specific cases, especially in algorithm reverse engineering, where you need to know, like, if I need to hit some check and there's a whole bunch of like constraints, anytime where you have lots of constraints, you can pass that or present it to Z3 and it can just like generate the answer like magically. So let's say you had an algorithm like something that was running and it checked your input and did a CRC checksum, like an Adler32 checksum. If you wanted to, you could just fuzz it over and over and over again, and you get checksum collisions quite often. But what you can do with Z3 is guarantee that every time you throw something, it generates something that will always represent the correct Adler 32 checksum or whatever else you're doing. So it ends up being a really, really cool tool. It's extremely helpful when you're reversing systems and need to format input very specifically to meet multiple constraints in a complex algorithm, right? Okay. I'll stop rambling now, but that's how you would solve it with Z3. And that's pretty much it. So thanks for watching.